13. On a small planet, an astronaut uses a vertical force of 175 newtons. So let's jot this down as we go. A force of 175 newtons to lift an 87.5 kilogram boulder. So the mass of the boulder is 87.5 kilograms. At constant velocity, so it's not accelerating, and it lifts it 0.35 meters above the planet's surface, so we'll call that h for height. 0.35 meters above the planet's surface. What is the magnitude of the gravitational field strength? So they want to know about the gravitational field strength on the surface of the planet. So this isn't planet Earth, so we know on planet Earth, g for Earth, that the acceleration due to gravity is 9.81 meters per second squared. Another way to think of this, right? Remember, we say F equals ma is the general form of Newton's second law. But when we're talking about the force of gravity specifically, we say Fg equals mg. And on Earth, g is 9.81. So think about what that really means. You could divide both sides by m, and you could get g by itself, and you'd find out that g equals Fg over m. And what would the units of that be? Well, the units of a force are newtons, so I'll just put that in brackets. And the units of mass are kilograms. So the units would be newtons per kilogram. Now really, what is a newton? A newton is kilogram meter per second squared. And this whole thing is over kilograms. So you could theoretically cancel the kilograms, and you'd be left with nothing but meters per second squared, which you would expect because that is the units of g. It's the original units of the acceleration due to gravity is meters per second squared. But what I'm bringing up is that another way to think about that is as newtons per kilogram. And when we think of it that way, and notice those are the units in all the answer choices, we're actually describing not so much an acceleration due to gravity, but we're looking at it as the strength of a gravitational field that an object is in. So you have this object, it's hovering now a little over a third of a meter above the surface of some planet. There's this gravitational field that's acting on it, and the strength with which that field acts is a certain number of newtons per unit mass of the object. So that's the idea here. And we can use this formula here, this g equals Fg over m, to calculate what g is on some other planet that's smaller than Earth. So if the planet's smaller than Earth, and Earth has 9.81 newtons per kilogram gravitational field strength, a smaller planet should have a smaller gravitational field strength. So we don't expect it to be the same as Earth, so we're kind of thinking it's probably not 3, and we certainly don't expect it to be bigger than Earth, so we don't expect it to be 4, so it should be 1 or 2. Now let's go ahead and calculate what it really is. So g for this other planet is going to equal Fg divided by m. Well, what was the force of gravity in this problem? Well, the force that they used to lift the object with a constant velocity was 175 newtons. And again, that was the vertical force exerted on the object, but it's equal and opposite to the force that the object is being pulled down with. So that's just enough to offset the force of gravity without accelerating the object. So the force of gravity is 175 newtons. And that's being divided by the mass of the object, which is 87.5 kilograms. And that equals 2 newtons per kilogram. So the best choice is 2. Also notice that the height never comes into play. It doesn't actually matter how far the object was lifted off of the planet's surface because it was done at a constant velocity. That's the key point, is that this force that was exerted vertically wasn't enough to accelerate the object. So it doesn't really matter how far it lifted it off.